Okay, I've got a quarter mole of nitrogen, and it undergoes a process from here, to this pressure, right? And in that process, I've got a work and a heat transfer given. Okay, so find the change in entropy. So the change in entropy, okay, I'm going to do this in molar form because they actually give me the number of moles. So it's going to be N times S2 minus S1, right? Which is essentially what I'm looking for. Now, I can look up S1 because I know the temperature. I need S2 to find that. Now, also know that I'm going to be looking up those S0 values in the table. So I actually am going to get that N times, and again, the equation that I'll use for this is going to be S bar naught 2 minus S bar naught 1 minus R bar times the natural log of P2 over P1. Because again, the values I'm actually going to look up are these S0 values, not the actual change in entropy that I'm looking for. Again, I'll be able to look up 1 because I have the temperature. What I need to do is figure out what state the temperature at state 2 is so I can go look that one up. And the way I'm going to do that is using the first law equation, which is going to be N times U bar 2 minus U bar 1 equals Q minus W. Okay? Where, again, Q minus W, that's, I know Q, I know W. I'm going to be able to look up U1, okay, and I can solve then for U2. So let me go ahead and look these values up to solve for U2. So again, I'm going to say N is a quarter mole, so 0.25, times U2, which is what I'm looking for, U bar 2, minus U bar 1. So this is where I'm going to grab my book and look up for nitrogen at 500 degrees Rankine what the value is. So I go here to table A23. I have nitrogen way over here. I go down to, 500 degrees Rankine? Go down to 500 Rankine. And I got U value and an S value. The U value is 2479.3, and the S value is 45.246. Okay, so first I'll use that U value. The U value was 2479.3. And again, I'm going to take this, set equal to Q, which is negative 125.9 minus a negative 500. Right? From this equation, then I can find U bar 2. And U bar 2 actually equals 3975.7. Okay? From this guy, I'm going to be able to look up S2, S bar not 2. Let me go ahead and jot down S bar 1, which again was 45.246. Let me go ahead and find this one. So again, now I know this energy. From this energy, I'm going to look up that entropy. So 3975.7. So I scroll down 3975.7. 39, and there it is exactly, right? This is at 800 degrees Rankine, but more importantly, the S value at 3975.7 is 48.522. Okay, so this is 48.522. So now I can go ahead and find my change in entropy. Delta S equals a quarter pound mole times S2, which is 48.522 minus S1, which is 45.246 minus R bar, which we want things in BTU, so that's going to be the 1.986. Now this time I don't divide by the molecular weight of air because again I'm given the number of pound moles. Usually I'm given mass. This time I'm actually given pound moles, so I don't need any conversion. R bar is what I actually use up. I use the the BTU one. And again, that's going to be the natural log of, that'll be 150 over 20. And when I plug all that in, I find that the change in entropy is negative 0.81, and this is going to be BTU per Rankine. So again, use those tables. Okay. First thing I do is first law to find what state 2 is. Then, knowing the energy at state 2, okay, I can look up the entropy at state 2. Knowing the temperature at state 1, I can look up the entropy at state 1. Okay. Then I'm actually getting that S0 value that I need to plug into here to find the actual change in entropy.